The Material Robotics Lab has published, enabling real-time shape sensing in soft robots via a miniaturized, single-signal, color-tuned optical sensor. This sensor, which we call Lumos, which stands for Light-Based Ultrathin Miniature Optical Sensor, is a compact, color-tuned, soft waveguide that translates bending and direction into vivid color shifts, enabling real-time 3D shape sensing and reconstruction. Its single-signal design allows seamless integration into miniature soft robotic systems, providing the shape feedback essential for closed-loop and autonomous control. Here we see Lumos' soft optical core, featuring a 1mm by 1mm cross-section being coated with thin, color-pigmented films that drive its characteristic color-shifting response. In addition, a thin outer waveguide is attached to the color-tuned core at its tip, enabling light transmission from the base of the waveguide to its distal end. A thin film mirror is then affixed to the distal end of the sensor, reflecting all the light that is sent through the thin outer waveguide back through the color-tuned core to be recorded at its base. Here we see the complete structure of Lumos. Light enters through that thin outer waveguide, travels to the distal end of the sensor, and is reflected back through the color-tuned core due to the thin film flexible mirror at its tip. On each side of the square optical core lies those thin, color-tuned films that enable directional and curvature-dependent color shifts. This configuration allows the optical signals to be both transmitted and received from the sensor's base, an essential factor in enabling a compact and fully miniaturized design. The color shifting phenomenon occurs as the sensor bends. Light concentrates on the side opposite the direction of bending, increasing its interaction with the thin film coatings. This interaction produces a directional color shift that encodes both its magnitude and direction of curvature through color. This is being shown here in both the blue and red color shifting directions. Lumos was then embedded into the neutral axis of a miniaturized soft robot, featuring 3 pneumatic actuators for omnidirectional bending. Optical inputs and outputs are routed directly from the sensor's base, enabling continuous optical feedback during its operation. This real-time optical feedback is shown here. As the robot is actuated in 3 different directions, the embedded Lumos sensor exhibits distinct directional color responses, visually encoding its deformation of the fully soft robot in real time, as shown in the top right video as it changes from red to blue and finally to green. To calibrate the signal response, the robot was actuated through its full 3D workspace, and the corresponding RGB outputs from the sensor were recorded at each configuration. A constant curvature kinematic model was used to extract the bending angle phi and curvature k for each position in space. 2 feed-forward neural networks, one trained to predict phi and another to predict k, were then used to reconstruct the robot's shape in real time, achieving a tip prediction accuracy of 0.47 millimeters. Here we observe the real-time comparison between the predicted and true shapes of the robot as it bends in 3D space, utilizing a real-time renderer to visualize the reconstructed shape in real time. The results demonstrate a close match between the measured and predicted configurations shown for both small and large bending curvatures, as well as during external manual disturbances. Using the shape sensing feedback, we performed closed-loop control to reach target points within the robot's workspace. Here we see the robot moving towards target shape configurations shown in white, while the predicted shape is displayed in blue. When the robot reaches the desired configuration, it transitions to green before proceeding to the next target location. This demonstrates real-time, closed-loop control, enabling the robot to autonomously reach designated positions in 3D space. In the final demonstration, the system was tested within an in vitro lung model, following predefined paths to reach targets on the left and right side of the soft mock lung environment, guided by the optical shape feedback. Lumos enables fully autonomous navigation inside this soft environment, where the robot successfully reaches both targets. An external feeding mechanism positioned above the lung environment drives the robot forward as it navigates first to the left lung target and then towards the right, where the larger bending deformations are required to reach the final target location. Through this series of demonstrations, we have showcased the full capabilities of Lumos, from its color-tuned optical design to real-time shape sensing and autonomous control within complex 3D environments. By embedding a single signal, direction, and curvature responsive waveguide into a soft robotic platform, Lumos transforms color into actional shape feedback, enabling precise and continuous control without external cameras or bulky sensing arrays. This work highlights a significant step forward towards fully integrated, miniaturized, and autonomous soft robotic systems, where sensing and intelligence are embedded directly within the robot body. Additionally, this sensor platform opens the door to future medical applications, where compact, soft, and intrinsically safe shape-sensing technologies could enable next-generation continuum robots for navigation, diagnosis, and minimally invasive therapeutic procedures.